So one sort of, not one, perhaps the governing equation one can use to describe electrochemical processes is an expression like this. Now what's actually hidden in this expression is a lot of complexity that we'll pull out in detail momentarily, right, in a few slides. But what this is basically saying is that the current at any given electrode, that is the net current, right, is going to be related to essentially current that's related to both anodic and cathodic reactions. So what you can see here is that there's some current here, J0. This is defined as the exchange current density, or if I had a given reaction, say I'm taking molecule A and reducing it to molecule B, right? There's going to be some equilibrium potential for that reaction, which we can look up in our tables as to what that value is. What the J0 value here is essentially telling you, or what is it? It's a measure of, essentially, is the exchange current density, which is referring to that if I sat my electrode right at the equilibrium potential, how much charge would essentially go, what is the rate of current flowing back and forth between the two charge states. So if I had ferrocene and ferrocenium, right, and I sat right at the equilibrium potential for those two reactions, this would be essentially telling me the rate at which electron is flowing back and forth. Now you have to realize, right, that if in fact I have a situation where you are at zero overpotential, what you will find though, right, is that you will not get a net current of J, right? So this is just telling you the value of how many times an electron goes from the electrode to the molecule, and then how many times the electrode from the oxidized form of that molecule comes back to the electrode. Or in other words, it's, if you will, kind of, because those two values will cancel, at the equilibrium potential, your effective net current, if you had equal concentrations of the two species, would be zero. But that doesn't mean there isn't a finite rate at which the electrons are being exchanged. Does that kind of make sense? It's like saying, if I'm at the equilibrium for a chemical reaction, are no molecules converting between each other? And that's not true, right? If I'm at the equilibrium for a given reaction, it just means the rate at which molecule A is going into B is equal and opposite the rate of the same rate as molecule B going into A. And so in net, the ratios are not changing, right? And that's the same way you should think about this, right? You have an electron as a reagent for A going to B. When I'm at the equilibrium potential, A is going to B, and the rate at which A is going to B is given by this exchange current density. But in net, right, the equal number of B are going back to A, and so the net current is zero. This value is then multiplied by things that will preferentially augment the rate in either the forward or the reverse direction, right? So the first term is referring to, let's just walk through the exponents here. So first you can see that the variation of the J will exponentially depend on this term overpotential, or eta. It's basically saying how much excess energy am I giving beyond the equilibrium potential value to drive this reaction in one direction relative to the other. And what you can see here is that because there's a negative in this exponent, if I apply an overpotential in one direction, or in other words, a positive value of overpotential, I will make this term go to zero, whereas I will make this term rise. And likewise, if I apply a negative value, it's this term that will explode and this term that will go to zero. And as a result, applying overpotential in one direction or another causes a preferential motion of the electron flow in one direction or the other. The way in which that overpotential impacts the current that you observe is related to these terms. Now, some you know, there's Faraday's constant over RT, and N is the number of electrons that are exchanged in this process. The A here refers to what's known as the transfer coefficient. So the transfer coefficient is saying what is the ratio of overpotential that's going into lowering the activation barrier for this reaction, right? Because what you're basically saying is I have electrons that can exchange from the electrode to a molecule. As I apply an overpotential, not all of the energy in that overpotential has to go into changing the rate of the reaction. Some fraction of it can. And you'll see in a moment that we'll actually be able to compute these for a given mechanism. So the transfer coefficient for a reaction allows you to infer something about the mechanism by which a reaction occurs. I won't belabor the remainder of this because we're actually going to dissect the mechanisms of what goes in this exponent and in the pre-exponential terms in gory detail in like a few slides. So I'm just going to kind of stop with this discussion and simply say that this is telling you how you can drive a reaction away from equilibrium by applying either a positive or negative exponential overpotential, and that overpotential is going to be related to current in a log linear fashion. Okay, does this kind of make some sense? Again, we'll go into this in gory detail. So what this is relating to, right, is that if I have a very, very high exchange current density, it's written as J naught there, here it's written as I naught, right? So if I have a reaction with a very, very high exchange current density, it's basically saying that both the I in the forward direction and or the J in the forward direction and the J in the backwards direction are large, right? And that means that I need to apply a relatively small overpotential to cause a significant amount of current in one direction or the other, right? And that would be designated by this sort of blue curve, right? If the exchange current density is small, right, then I need to apply a pretty substantial overpotential to be able to compensate for the fact that the J0 value is low. Remember, the exponential value is going to cause one of the terms to go to 0 and the other one to explode. But of course, if the J0 is a very, very small value, to measure an appreciable amount of current, I need to make the eta very large. So eta and J0 essentially track anti-parallel with each other for a given J, right? So if I have a low J0 and I want to observe a given current, I need to apply a high eta. If I have a very high J0, I can get the same current by applying very little eta. And that's kind of reflected in these two, right? Okay. The other way to kind of view this, right, is that if you have a reaction with a very, very large overpotential, so we're only looking at one side, you can see that as you change the I0, you systematically augment the actual current that you're observing. But it can be correlated insofar as if I had, say, a different catalyst or a different material that had a different I0, right? I could always get the same current by simply compensating for that I0 by going to a larger overpotential. In other words, the red curve would have the same current as the blue curve if I simply extended this line to greater overpotential. Now, the other thing you should appreciate, of course, is that changes in I0 are going to appear as linear changes in the current you measure, whereas changes in overpotential are going to affect the current in a logarithmic fashion, right? So this is kind of the difference between the intercept of the curve and the slope of the curve. And the slope of the curve is really given by how you vary the current by the overpotential that you apply. We'll come back to that. Okay. So it's from this that I'm actually going to kind of walk through how you can understand the overall shape of what, if any of you have collected in a piece of electrochemical data, a reversible outer sphere one-electron reaction looks like. So you get essentially the shape that looks like a duck. I'm walking through this now not because a duck is easy to understand from an electrokinetic perspective, but rather that a duck is usually characterized of the most elementary type of reaction, which is simply an outer sphere one-electron transfer. So what you're doing in this type of a measurement is you are sweeping the potential. So that means that in time you're varying the driving force for electron transfer. And so there's going to be at some point where you're so far away from being able to drive, say, a reduction in this case, that I'm not going to observe any current. But as I start to approach the potentials that are necessary to reduce the molecule, I can begin to observe current associated with them. Now, one thing that should be noted actually is that the equilibrium potential, if you collect a piece of data like this, is given by the average essentially between the peak potential here and the cathodic peak potential here. So does anyone want to hazard a guess as to why I'm observing reduction current before I get to that half-wave potential? In other words, why am I able to reduce the molecule before I get to the equilibrium potential for reducing that molecule? I should say something about the experimental conditions here. In this experiment, I have only the reduced form.
Because you're
Q is different. The Q is different because the reactants are in large excess. So when we define an equilibrium potential, right, we're defining it for equal chemical activities of the things that live on both the reactant and product side of the equilibrium. But if I set up my electrochemical cell where I have only the reactant, of course it'll be easier to do the reaction, right? And easier to do the reaction means that we observe current at earlier in potential than we would need to drive it otherwise if I had equal populations of the two, right? And so anyways, you observe current before you actually get to the equilibrium potential. That current is due to this reaction, oxidizing the reduced form of this molecule. As you then go further in overpotential, of course, the rate of the reaction is increasing because you have additional driving force. The other thing that should be said here is that for a reversible voltammogram here, you're actually assuming that the equilibrium concentration of the electrode will always reflect the potential that you apply. In other words, you get reversible voltammograms when the rate of the electron exchange is essentially very fast relative to the rate at which you're sweeping the potential. In fact, I think you'll do some experiments where you actually look at this and you vary the rate at which you sweep the potential in order to diagnose something about the rate of electron transfer. Eventually, you're going to get to a point as you ramp the potential where you're going to run into a different problem. And this different problem is, now I have ample driving force to oxidize or reduce whatever molecule comes to my electrode. But of course, because I'm at a surface, right, I may no longer be limited by the rate of the ET, but rather be limited by the rate of molecules coming to the surface. And as a result, there's going to come at a time where you're going to deplete quite significantly the number of the reactants at your surface. In other words, you can think of it as that you're creating a zone of depletion. Or in other words, if I have a surface like this and my electrode is right here, I'm going to create over time kind of an area near my electrode where there's simply not going to be any stuff. And so I'm going to have to wait for new reactants to come in from outside. And as I do electrolysis for longer and longer, the sphere over which there is a depletion is going to grow and grow and grow. And as a result of it growing and growing and growing, as you can see, as I increase the polarization potential here, remember, moving in this direction is not only moving in this direction in voltage. Because I'm doing a sweep, moving in this direction is also moving in time. It's a really important thing to appreciate, right? Because I'm doing a linear ramp of the potential, this axis is not only a potential axis, it must simultaneously be a time axis. And after I get to sufficient driving force to essentially instantaneously reduce or oxidize any molecule that gets to the surface, the additional potential doesn't quite matter. What matters is just how much time I've spent past the wave, and that time translates into a decay in the current simply because I've actually created a larger and larger sphere of emptiness, of loss of the material. And that's why, actually, the current continues to decay even when I switch the potential. Right? Because when I switch the potential back, even though I've decreased the driving force for ET, I've increased the time that I've had to deplete the molecules. You can see that here, right? After I switch the potential, I'm going back and I'm decreasing the potential applied. If I'm decreasing the potential applied, I must have created less driving force for the molecules to be oxidized. However, because I'm past the wave here, I have ample driving force irrespective of what these potentials are. So all that really mattered is that I happen to spend more time. In fact, this curve, this line here, if you fold it over on this side, is literally the extrapolation of this decay. That's actually all it is. The only place where situations get into a difference is when you actually go back and you get to a potential where you're able to now re-reduce the oxidized form. So because I've made this depletion zone of the reactant, I must have made an amplified concentration of the product of the reaction. And if there's an amplified concentration of the product of the reactant near my electrode, when I go back across this curve, I now have the ability to back reduce that oxidized form. and that's at high concentrations of the electrode, and that's why, again, you observe reoxidation current occurring before you reach the equilibrium potential. Right? Because near the electrode, which is all my electrode really cares about, I have a lot more of now the oxidized form than the reduced form. So again, the reaction quotient has been shifted, but shifted in the opposite direction. And so when I go back along this and I have the ability to re-reduce that oxidized stuff, I get current in the opposite direction, and eventually it crosses the zero line and I get net oxidation current, or I guess in this case reduction current, as a result of re-reducing that oxidized stuff near my electrode. And then once I go again to that peak, I now have created a depletion zone of that oxidized form. In other words, I made it look a lot more like the starting situation. And so I again get a decay, and this decay is simply now related to the tiny bits of oxidized form that I made here that have to travel back to the electrode to get re-reduced. There's a lot going on here, and we will again go through this again in a slightly different way that may help to explain this in a little bit more detail.
I think it's important for students to recognize that the x-axis of potential is flipped here from what they've seen in experiments.
Yes.
So yeah, going left here is actually going more positive, which is oxidation, which is the exact opposite of what we've seen in experiments in lab.
Yeah, that's really important to appreciate. So sadly, electrochemists adopt two different conventions for how they plot acids. I really wish the community would have some big convention and then they would just sort this out and everyone would agree. In the lab, I think we'll adopt IUPAC conventions, and as a result, the way IUPAC conventions essentially work is that as you scan in this direction, you'll do oxidation reactions, and current that is above the zero line corresponds to anodic or oxidation current. Here it's flipped. You see here this has EPA. A refer to anodic. Normally, like the real way to take this curve and make it look like everything you'll see for this same reaction is to literally rotate by a C2. So if you take this CV and do a C2 rotation on it, you'll get the CVs that you actually collect in lab, right? And literally, right? Because what will then look like an anodic curve, right, will upon C2 look like an anodic curve plotted in the positive direction, and then your cathodic wave will be in the negative. Right?
What's the C2?
Oh, sorry. Just a 180-degree rotation around the center of this. So it's literally like taking that whole plot and just rotating it by 180 degrees. Yeah. It wouldn't matter whether you did it clockwise or counterclockwise. Yeah.
So this is maybe a stupid question because I haven't done any of the labs for this yet, but what do we learn from this other than like IPA and IPC?
Great. So for a reversible couple, collected in the limit, the rate of the reaction is reversible, it's fast relative to the rate of scan. All you really learn is the equilibrium potential. So this is often used as an analytical tool to diagnose what is the potential of R to O for some unknown R and O. Right? If I didn't find it already in a table, I could measure it to determine what that is. If you vary the sweep rate, you can then determine the rate at which electrons go to R. That might teach you something in addition to that. But I have to say, the reason I'm actually discussing this right now is that while there's a lot of rich complexity here, this is the most boring cyclical thermogram you could ever collect in the context of energy conversion, right? So what we're trying to do here is connect these kind of elementary ideas of electrochemistry to how they actually relate to problems in energy conversion. But if you wanted to really convert energy, you're usually making bonds. So there are multiple electrons transferred, and you will not get something like this, right? So if you see this, you learn something important, the reduction potential. But what you sacrifice is sort of all the rich chemistry that you're hoping these electron transfers can be coupled with. Okay. So this is kind of what that's related to. For any given process, right, if I scan faster, what I will essentially do is move my applied potential faster than the rate of ET can keep up with it. And as a result, these waves will essentially broaden out. So what I'm showing here, right, is that as we increase the scan rate, these peaks are moving away from the equilibrium potential, both on the reducing leg as well as the oxidizing leg. Right? And that's basically saying I have a wave here. The wave is related to me moving the potential. And in the reversible limit, what I'm saying is that as I move the potential, the electron transfer is so darn fast that it's able to keep up with every little step that I'm making in the potential. But here, I have a situation where as I move the potential, if the rate of ET is sluggish, then I have to actually apply more overpotential to be able to get the same current. And as a result, the two waves essentially spread out. Does this kind of make sense? Yeah. Okay. All right, that's two things that relate to processes where you will observe both the forward and backward reaction in the same excuse me, in the same cyclical chemical. What I'll spend the remainder of the time in this lecture talking about is what actually will comprise the bulk of kind of the studies that you'll be doing, which relates to irreversible electrochemistry. Essentially, when you're using electrons to drive the rearrangement of chemical bonds in some irreversible, oftentimes energy storage or energy releasing type of reaction, right? And this is a broad subfield, if you will, of electrochemical kinetics, right? So here we're trying to understand how the electron as a reagent can be used to drive reactions. And what we're really interested in is how does changes in the applied potential change the rate of that reaction? And how can we construct materials and molecules that exploit that overpotential current relationship in a productive fashion to store energy with the minimal loss of additional energy? So that's basically the goal. Okay, the way I like to describe this really is that in an irreversible electrochemical reaction, the kinetics that you know about and learned about and even investigated in, say, Module 2 are no different than what we're looking at here, right? It's just that electrochemical reactions are like all chemical reactions, they just have a few additional caveats. So what I'm showing in this graph is a relationship between applied overpotential, you can think of it as overpotential, with 0 being where some reaction occurs at the reversible potential, right? So say you have a reaction, and this would in fact be the case for taking protons to H2, where the potential that is the equilibrium value has been determined to be 0 volts. Right? In fact, we use that as convention of being 0 volts. So this is a reaction where you're taking protons to H2, and along the way you're making an HH bond. That's clearly a lot more complicated than simply transferring an electron outer sphere to a molecule. Right? And as a result, this is something that will require an overpotential on almost all catalysts except platinum, right? Which happens to do this reaction reversibly. And as a result, right, what I'm going to plot here now is on the y-axis, the steady state current density, right? So this is essentially that J value you're measuring. But because we're doing a catalytic reaction here, right, we're going to assume for the moment that this is just not even a sweep, right? So we're taking away any issues of how fast I'm moving the potential. The way I would get a curve like this is I would look at the current I'm measuring, and I'd simply step to a new potential. And each time I step to a new potential, I'd wait until the current was time invariant. Or in other words, the reaction reached a steady state. And then I would record that steady state current here, and I would expect to get these sorts of curves. What are the regions in these curves? So first, if I apply very little overpotential, I have very little driving force for the reaction, and therefore I don't get any current. That's why the current line is very, very low here. If I apply more overpotential, I'm going to be able to drive the reaction faster, and as a result of being able to drive the reaction faster, I should increase the amount of current that I see in my electrode. Importantly, in this region, I'm designating that while I've increased the overpotential, I haven't increased it so much, and so what I'm really expecting here is that the microscopic rate of these bond rearrangements at the surface will still control the overall rate. I won't be limited by, for example, the rate of H2 or protons getting to the surface. But if I apply a lot of overpotential, I can get into a region where I will be limited by the rate of H2 coming to the surface or protons coming to the surface. And then if I apply even more overpotential, I will be purely limited by the rate of mass transport rather than the rate of what we call activation control or the rate of the microscopic steps. right? And so in a world where I have things coming to the electrode at an infinite rate, this is only a thought experiment, right? There's no such thing as moving mass at infinite rate. But if I could move mass at infinite rate, the dotted line is what I would expect, right? Because the expression has an exponential term in eta. So as I increase eta, right, the current actually rises in essentially an exponential fashion. This would literally go, it would continue unabated, right, to an infinite value as long as I can move mass at an infinite rate. But of course I cannot move mass at an infinite rate, right? And so when I get to a very, very high expected activation controlled current, I'm no longer limited by that, I'm simply limited by the rate of moving stuff to the electrode. And so the real current I measure is some value lower than that activation controlled value. And in fact, when I get to very, very high overpotentials, you find that the current is now independent of applying more overpotential. Because even if I make the activation control rate higher and higher, it doesn't matter. It's just how fast I can move molecules to the surface. Does this kind of picture make sense? So if you can understand these sort of four regimes, you'll understand a lot about how we think about electrochemical kinetics in these systems. Here's also how you can understand a little bit about how sweeping the potential impacts this. So if, for example, I sweep the potential, right, and importantly, I'm only talking about Faradaic current, or current going into the terminal reaction in this case, what you'll actually find is that depending upon how fast I sweep the potential, I can actually have a higher than expected concentration at my surface because I'm not at steady state. I haven't reached the steady state condition, and so if I have a lot of reactant or a lot of protons at my surface, I'll actually get a peak in that curve, and then it will eventually decay to the steady state value. And that decay is the same decay we saw before when we just did a simple outer sphere 1 electron transfer. The same would exist for a complex multi-step reaction as well. And that's why when I go back, right, because I've spent more time here, I don't retrace this peak. I instead just go along that flat line that I had before. In other words, this return curve is more diagnostic of the steady state than that initial curve because I have a transient. I'm moving the potential in time. Okay, does this sort of make sense? Okay. The last little piece is that not all the current at your electrode, remember, is going to go towards the terminal Faradaic reaction. In order to apply the potential in the first place, I need to have some of the current accumulate at the surface with ions accumulating in solution. Or in other words, the electrode is behaving like a capacitor. And so in order to charge up that capacitor, I'm going to have to pass a certain amount of current associated with that. And that's why there's a splitting between the forward and reverse traces that's simply related to that capacitance. So what all is going on here, right? On some level, this is simply a reflection of all the individual terms we looked at the beginning of the lecture yesterday, right? That we need to worry about things like how fast are things coming to the electrode. We need to worry about how we're changing the driving force for the reaction. And we need to worry about whether charge is going to the reaction we expect or going to simply charging the double layer. And the tough thing about electrochemistry is not that each of these individual processes are hard to understand. It's just that all of them are occurring at the same time. So that's the tough part about understanding electrochemical systems, is that they tend to all occur at the same time. In fact, most of the way in which we do experiments is to try to construct, essentially play tricks on the system, to try to isolate one of these effects apart from the others. Right? In other words, isolate the rate of activation-controlled chemistry rather than the rate of mass transport. And there are tools we can use to do that. We'll do that both for molecular catalysts as well as surface catalysts. And then the other thing we may want to do is collect data at steady state so that we can exclude this double layer current. Right? So there are these tricks we can play to kind of understand and tease out the system. Okay, so let's just go back a little bit and try to understand why does changing the orbital potential lead to a logarithmic relationship. So let's take a complex reaction, like taking water to O2 with 4 electrons and 4 protons. If I apply a substantial overpotential, the back reaction doesn't matter, right? Because I'm very far away from the equilibrium potential value. In this limit, if I collect data at steady state, the current density or the current is simply going to be related to the rate of producing O2, or the velocity of the overall reaction, simply by a proportionality constant, which is n, the number of electrons transferred, and Faraday's constant. This is a very, very simple relationship, but a universal relationship that will hold in steady state. If this is the case, I can collect steady state data as a function of varying the overpotential, and what you'll get is what's known as a Tafel plot, right? A Tafel plot is really any time that you're plotting activation-controlled rates or rate constants relative to an applied overpotential or an applied potential. And what you find oftentimes is this sort of linear relationship between, or log linear relationship is more precise, right? I'm varying the potential in a linear fashion, but I'm varying the current or the rate in a logarithmic fashion. This we know to be true from the Butler-Volmer equation, but another way to view this is in terms of Marcus theory, which we talked about in inorganic chemistry a little bit. Did we do a lecture on Marcus theory? Maybe we did. We will in 504. So what Marcus theory relates to is that for any electron transfer reaction, the barrier to that reaction can be described by the intersection of two parabolas. And the intersection point relative to the bottom of these parabolas is going to give you the barrier to the reactions. As you increase the overpotential, what you're essentially doing is changing the energy of one of the reactants, and some fraction of that overpotential is going into lowering the activation barrier for the reaction. And this is why you get a logarithmic change in the rate, and the last piece of this, of course, is that if I change delta G double dagger in a linear fashion, I'm going to get a logarithmic change in the rate constant. And that's why changing overpotential in a linear fashion gives rise to a logarithmic change in the rate. Okay, you can extract something out of the slopes of this, and we'll walk through that in detail momentarily. Okay, so let's take a simpler case where we have 2 electrons plus 2 protons going to make H2. In this situation, people have mapped this reaction on a lot of different metals, and they've looked at the exchange current density as a function of the binding energy. But what we want to really understand is what is the mechanisms by which this reaction could occur. So say I have a metal surface, right? I could envision several types of mechanisms that are possible. So if I have a metal surface, I could have as the first step binding an electron and a proton to make a bound H atom on the surface. Then I can have 2 possible follow-up reactions on the way to making H2. I could have another electron and proton react at that surface site to make H2, or I could recombine this surface H with another surface H on the electrode somewhere else. And that would simply require that these 2 H's migrate across the metal surface. And to a large first approximation, these 3 steps are the only real viable ones you can write for making hydrogen from a metal surface. There may be additional complexity associated with how many of these intermediates there are, but we must know that making H2 proceeds through the intermediacy of a surface-bound H. So the question is, though, if I have these 3 possibilities, what might be limiting the rate? And how can we do experiments that might inform us about what might be limiting the rate? So let's consider the first possibility. Say we postulate that the first one is rate limiting. If the first one is rate limiting, what is the rate law for this mechanism, right? So whenever you write a rate law, right, you worry about what are the reactants and what's actually existing in the transition state, right? What are the participants in the reaction, right? And so what you can essentially write is a rate expression that looks like this. So the Butler-Volmer equation tells you, right, that there will be an exponential dependence on the applied overpotential, right? And so I have an exponential term that I'm using this beta because this is, well, we can talk about that in detail later, but this is an elementary reaction, so electrochemists use the term beta rather than alpha. But nonetheless, this is a transfer coefficient, or it's saying what fraction of the energy I'm putting in is going into changing this rate. So I have a beta A to F over RT as an exponential term, but I have other participants in this reaction, right? The surface site has to participate, so I need to know what the surface coverage is of those active sites. But I also need to know the chemical activity or the concentration of H+, because H+ is also a reactant in this equation. So I get a rate expression that's related to a rate constant, a surface coverage of active sites, or a surface concentration of active sites, the concentration of protons, and an exponential term that essentially comes from the Butler-Volmer equation. Now, if I want to look at how this is related to the overall reaction, remember this is only giving me the velocity of this elementary step. But every time I go through this elementary step, by definition, I have to go all the way to the completion to regenerate this site. So kind of imagine this like you're, you know, at a, like really any reaction, but imagine that you're at a, you know, an amusement park, right? There's often a choke point in the line that gets you to the roller coaster. But every time you get through that choke point, you are going to ride the roller coaster and come back out on the other side. And as a result, every time these protons and electrons go through this sort of choke point, they're going to go all the way through the other end. And as a result of that, I'm going to transfer 2 electrons times Faraday's constant to give me the overall current. So all I'm doing here to translate the rate of this reaction into the current of the overall reaction is appreciating that every time I go through this step, I have to pass 2 electrons. And NFV, the velocity of the reaction, gives me the current. So if I have an expression for the velocity of the reaction, I have automatically an expression for the current. And that's simply 2F times this entire term. Now, what are we plotting in a Tafel plot? Well, what we're plotting in a Tafel plot, right, is essentially the ratio or the slope of variation in the overpotential with respect to variation in the logarithm of the current. And what you can see, though I haven't gone through the math here, essentially, is that if you rearrange this by taking log of j and then log of all of these terms, remember the log of things that are multiplied by each other just become independent sums. And the log of this term, right, simply becomes its expression, beta eta f over RT. So if you take the derivative of eta with respect to log of j, by rearranging this expression in log form, what you actually get is this expression. Because this is an exponent with base e, the log has this 2.303 term. So what you find is it's 2.303 RT over beta f. And if the transfer coefficient is approximately 0.5, as you find from Marcus theory it typically is, you get essentially a slope of 120 millivolts per decade. And that's because this is literally plugging in terms, right? So 2.3 times the gas constant R times T, the temperature at room temperature, over F, that term is always going to equal 60 millivolts per decade. And if beta is equal to 0.5, 60 over 0.5 is going to give me something around 120. Right? If beta were slightly different, this value would be different. What would be the expectation for the reaction order in proton? If I vary protons, how am I going to change the rate? Is it going to be in a first order fashion, in a second order, in a first order fashion, right? And that's because the exponent on the proton is 1. Right? In other words, if I vary the proton concentration by 1 order of magnitude, I expect the current to change by 1 order of magnitude at a constant overpotential, or a constant. Realistically, it should be constant potential. That's a subtlety that we can talk about later. Okay, so if this is in fact the case, this has actually been observed experimentally for certain metals, where you in fact get at room temperature essentially the expected slope. This happens to be mercury. And mercury gives this exact behavior. For rate limiting, in the initial step of putting an electron and proton on the surface is rate limiting. And that rate limiting step gives rise to this very, very well behaved slope that's essentially exactly the same as what you predict from this, this sort of very, very basic analysis. Now this is always incredibly shocking to me. So this was actually discovered by Julius Tafel accidentally in 1905. This is why we call these Tafel plots. And it's kind of remarkable, right, that you can take a complex surface like mercury and have it predict for you with just, like, 30 seconds of pencil and paper math what the expected scaling of overpotential and rate should be, right? And this works remarkably well over a remarkably large range. So you can't, this is a little blurry here, but this is a variation in rate by approximately 4 orders of magnitude. And yet this relationship holds remarkably. This is not the only mechanism we can envision. What if instead we have an equilibrium in the first step? So the first step is no longer rate limiting, but we postulate a different mechanism where the first step exists in quasi-equilibrium. And then is followed by a rate limiting step where electron and proton react with the surface site to make H2. in this sequence, you can convince yourself that the rate expression is always going to be equal to the velocity of the rate limiting step. Now, the rate limiting step now is dependent not on the surface concentration of just metal sites, but is instead related to the surface coverage of these key intermediates. Right? So we have now a rate constant K2 for this step times the surface coverage of H times now again the concentration of H plus in solution, because that's a participant, and we have that same exact exponential relationship in beta A to F over RT. But because this H here is an intermediate, this is not a valuable rate expression for us, right? Because we don't know whether there's a dependence of this H on potential. So the way we rewrite this is we write an expression that's simply an equilibrium expression for this reaction. And that's simply saying that the ratio of the concentration of those surface H's to the ratio of vacant metal sites up above is going to be given by an equilibrium constant, the concentration of H plus, and an exponential dependence that's simply A to F over RT. There's no beta in this exponent, right, because this is an equilibrium expression. It's not a rate limiting step. And as a result, every increment in overpotential is going to shift this equilibrium by an equal amount, just like the Nernst equation would tell us. In fact, you can come up with this expression by simply appreciating that all we're doing is products over reactants, right? And so products is theta H over reactants. What are the reactants? The reactants are proton, metal H, and an exponential term. And so simply by rearranging that, we get this expression. Okay, so if I have this expression, I can plug it in essentially into this expression for theta H. And what I get out of here is a combined expression now for what my expected behavior would be. But the thing to appreciate here is that there's an exponential dependence that came out of the variation in the concentration of theta H, as well as an exponential expression that related to the way in which potential alters the rate of this reaction. In other words, we get an additional bang for our buck in changing potential, because changing potential changes the position of this and the rate of this. And the combined effect means that in the exponential term, we don't just have a beta, we have a 1 plus beta. We also have another thing that's important to appreciate. Because proton is involved in this step, and proton affects the equilibrium here, we actually have now a second order dependence in the proton activity. So if I vary pH here by 1 unit, I should not expect 1 unit change, 1 decade change in the rate of the reaction, but rather 2 decades of change, because I have a second order dependence in proton. And in the exponent, we have a 1 plus beta. Again, if you rearrange terms here, you'll find now that you get this 2.3 RT over F. That term is that same 60 millivolt per decade term that we had before, but now you're dividing not by beta, but 1 plus beta. And so you actually get a radically different tafel slope, something on the order of 40 millivolts per decade rather than 120. And it's simply a reflection of the fact that my potential is giving me twice the bang for my buck. Okay. This sequence can also change, though, if I assume that this reaction is in major equilibrium. So the sequence previously, right, was assuming that I wait and I put 1 proton on, and that's in minor equilibrium. Most of the sites are still vacant metal sites. But as I apply the potential, I'm changing the population of a minority equivalency of H's on the surface, and then I'm protonating them off with another electron to make H2. If instead I designate the scheme as having an electron and a proton, but this now is fully covered in H, I would get a totally different sequence, right? So here again, the rate expression is the same, which is the velocity is dependent on this surface coverage, the activity of proton in this exponential term. But importantly, if the coverage of H is very, very high, varying the potential will not change this by very much, because I can only pack on a certain amount. If I'm completely done with packing those on, I can't change the concentration by very much after that. And as a result, I simply get this overall expression, and I return back to an expectation of 120 millivolts per decade. Again, this comes just out of rearranging these terms. So how do you distinguish between these two, right? We have 2 different mechanisms that are indistinguishable insofar as the expected tafel slope. And the way you can tell, right, is that if this is indeed the case, the surface coverage of H would be very, very high. And so you can often use spectroscopic methods to determine whether that's the case. And so oftentimes you need to combine electrochemical data with spectroscopic data to be able to put together a mechanistic model. Right. Okay, the last possibility, right, is a situation where H's recombine to make H2. And in this sequence, right, the rate of the reaction is actually fairly simple to write out because the rate limiting step is simply a K3 times the square of the concentration of those surface H's, because two surface H's have to come together to make H2. Just as before, if we assume that the pre-equilibrium step is in minor equilibrium, I can write an expression for the ratio of these H's on the surface relative to the ratio of the vacant metal sites. And that's simply going to be related to that big K1 times the activity of H, and now an exponential term again that lacks that beta because this is an equilibrium process rather than a rate limiting process. And so if I rearrange terms here, we again get this expectation that there's a second order dependence on proton, there's a second order dependence on the availability of those metal active sites on the surface, and now in the exponent we don't have 1 plus beta or beta, we instead have 2. As a result, if you rearrange this expression, you find that you don't get a 40 millivolt Tafel slope, you don't get a 120 millivolt Tafel slope, but you in fact get the lowest possible Tafel slope for a 2-electron reaction, which is 30 millivolts per decade. That's the other thing you can know as a good universal rule. You can never get a Tafel slope that's lower than the overall reaction, lower than 60 divided by the number of electrons transferred in the overall reaction. So if I have a 4-electron overall reaction, like oxidizing water to O2, the lowest possible Tafel slope is 15. Right? If I had an 8-electron reaction, in principle, the lowest Tafel slope would be 60 over 8, for example. In point of fact, most catalysts never are able to achieve that limit, because it would mean then that the rate limiting step would be very, very late in the sequence. And oftentimes the rate limiting steps are much, much earlier in the sequence. Again, as before, we saw that there would be a second order dependence in H, and that's exactly what we also observed here. It turns out that platinum electrodes, which happen to do hydrogen evolution reversibly, actually exhibit this behavior. So their Tafel slopes are on the order of 30 millivolts per decade, and that's because it's thought that they proceed via this type of mechanism of combining two H's to make H2. Okay. I think that's where I wanted to stop. It did, unfortunately, take the entire time, but there's a lot here. It's all recorded, but I really, really encourage you, because I want everyone to try to have some intuitive grasp of this, is to come talk to me or to come talk to your TA to try to understand these concepts as best you can. And you'll see them recur as you actually do various things. All right, thanks, everyone.